Terry Vance, World Top Fuel Drag Racing Champion, 9-time Pro Stock National Champion, Byron Hines, the mechanical genius that made Terry Vance the fastest man on two wheels. Over 203 miles per hour in less than 7 seconds. Together, Vance and Hines have won more races than any other team in motorcycle drag racing history. The high-performance products and techniques that you are about to see represent years of hard work, setting a new standard of excellence. A standard of excellence that is necessary when your name is on the line. Byron Hines will start with a brief review of the parts and modifications necessary to assemble a high-performance engine.
The crankshaft should be checked for straightness. It should then be cleaned, and to eliminate any chance of twisting, heliarc welded at 8 points on the rods and mains. After welding, recheck the crankshaft for straightness and install a heavy-duty cam chain. Check all transmission bearings and gears for cracks and wear. To keep the transmission from jumping out of gear, we undercut second and third gear. The process involves backcutting the engagement dogs and the receiving slots. Heavy-duty transmission bearings are also recommended for use in a high-performance engine. Because of the increase in power, a stock clutch hub often breaks down and must be replaced. The Vance and Hines Super Hub consists of a modified stock hub with 6 heavy-duty springs and 3 heavy-duty rivets. The clutch hub is reassembled with a billet backing plate. Then it is welded and then balanced. Vance and Hines oil pump gears increase oil volume flow about 30%. They are highly recommended for high-performance engines. Using a Vance and Hines 1168cc kit, the cylinder assembly is bored and finish honed using a 500 grit stone to allow a running clearance of 2/1000 of an inch measured at the bottom of the piston skirt. The bottom of the sleeve is then chamfered to make ring installation easier. The cylinder is then surfaced to make sure it is flat, removing as little material as possible. We have chamfered the tops of the pistons, allowing us to use a stock head gasket. Check the ring end gap at the bottom of the cylinder to eliminate any scratches in the combustion area. The ring gap is set at 8 to 10/1000 of an inch on the top ring, with 8/1000 on the second, and 5 to 10/1000 on the oil ring rails. Install all rings with the numbers or marks up. Make sure that the oil ring expander is butted with no overlap. Once the rings are installed on the pistons, the cylinder is ready for installation. Completely disassemble the cylinder head and check for flatness. Also check the valve guides for wear using the method recommended in your service manual. A 3-angle valve job is ground using angles of 37.5 degrees for the top cut, 45 degrees for the actual valve seat, and 55 degrees for the inside bottom cut. For maximum performance, the 45-degree cut should be to the outermost edge of the valve. The final width of the seat should not exceed 30 to 40 thousandths. Lap the valves with a fine lapping compound. After the valve job, we blend the edge of the port with the valve seat. Springs are then installed using a standard Vance and Hines valve spring kit with aluminum collars. At this point, the rocker arm oilers need to be ground off for cam lobe clearance. Also check for rocker arm wear. And remember, take extra care to clean the valve guides when reassembling the cylinder head. The cams that we'll be using in this engine are the Vance and Hines part number 12042. They are 345 thousandths lift at the valve on the intake and exhaust. The duration has been increased to 248 degrees, measured at a 50 thousandths checking point. This will be explained more fully in the degree section. We will use a dyno ignition and axle coils because they are very reliable. In our racing applications, we use Pro 1 oil. Its synthetic qualities help reduce friction and generate more power. We will now review the steps necessary to assemble a high-performance engine. During engine assembly work, make sure you use an assembly lube on all moving parts. Once the cases have O-rings and snap rings in place, the transmission and crankshaft are ready for installation. Now, bolt the bottom half of the engine case on. After the oil pump has been bolted in place, Vance and Hines high-volume oil pump gears are installed. Next, the clutch hub is installed. When installing the clutch hub cover, make sure that you do not use a 40mm bolt in the position that a 35mm bolt is required. Using the wrong bolt will cause severe clutch hub damage. With the engine upright, the cylinder and pistons are now ready for installation. The pistons are installed onto the rods. After installing the wrist pin clips, a special tool is used to keep the pistons from dropping. When installing the cylinder, make sure that the dowels and the base gasket are in place. Take extra care and do not overlap the oil ring expander or damage any of the rings. The head gasket is now ready for installation. When using a stock head gasket, no sealer is needed. But if you are using a copper one, a very thin coat of sealer is added before installation. Keep making sure that the dowels are in place. Lower the cylinder head down and torque. Using Vance and Hines heavy-duty cylinder studs, start at 20 pounds pressure and increase at 5-pound increments until you reach 35 foot-pounds. Camshaft installation and degreeing are the most important and difficult steps in building a high-performance engine. Extra care should be taken to complete the following steps thoroughly and accurately. To begin with, we will be using a positive stop method to find top dead center. Sighting through the number 1 plug hole or using the stock advance unit, arrive at an approximate top dead center on cylinders 1 and 4. Install the degree wheel on the dyno side of the engine. Make a pointer of wire and position it above the degree wheel at the 0 position. Then rotate the engine away from top dead center. Using a positive stop made from a spark plug, install it in the number 1 cylinder. Then bring the piston gently back up until it contacts the positive stop. Now take a reading on the degree wheel and make a note of it. Then rotate the engine in the opposite direction until it makes contact with the positive stop again. Take a second reading and make a note of it. Our reference point is 1/2 of the sum of the 2 readings you have obtained. In our example, if our first reading was 20 and our second reading was 25, the sum of the 2 readings would be 45. We divide 45 by 2 and get our reference point of 22.5 degrees. With the positive stop against the number 1 piston, move the position of your pointer to your divided total. In our example, 22.5 degrees. Now rotate the engine in the opposite direction until it contacts the positive stop again, and your reading will be 22.5 degrees in this example. If not, redo the above steps. Remove the positive stop, and watching your degree wheel, you now can position the motor exactly at top dead center by rotating the motor so the pointer is on 0. Install the cam sprockets onto both the intake and exhaust cams with the cam sprockets positioned in the center of the slot. Make sure that the sprockets are in the proper position and not 180 degrees off. Only 1 bolt, tightened snugly, is needed for degreeing. Before you begin the degree process, completely lube all the lobes of both the intake and exhaust cams. With the engine at top dead center on cylinders 1 and 4, carefully bolt the exhaust cam into the stock position. Refer to the existing stock timing marks located on the cam sprocket. After the exhaust cam is bolted into place, the number 1 arrow will be parallel to the valve cover gasket surface. With the exhaust cam in position, the intake cam is now ready for installation. From the exhaust cam sprocket number 2 arrow, count 20 pins on the cam chain. Then align the intake cam sprocket number 3 arrow with the number 20 pin. With the cams in the proper position, the exhaust cam number 1 arrow will remain parallel to the gasket surface, and the intake number 3 arrow will be 90 degrees from the gasket surface. Next, recheck your degree wheel to make sure it is at 0. If the cams are in the wrong position, turning the motor over will bend the valves, so make sure you have installed the cams correctly. At this point, all the cam caps should be torqued to 85 inch-pounds. Install the cam chain tensioner, and with manual adjustments, remove any excess chain slop. Carefully rotate the engine through to enable the adjustment of the valves. If any resistance is felt, stop immediately. Something is wrong. If the engine rotates properly, adjust the valves at 6/1000 of an inch clearance. The cams are now ready for degreeing. To begin the degreeing process, you need to set up a 1-inch sweep dial indicator. A base can be easily made from a metal strap, drilling a 1/4-inch hole in one end. Bolt your base to an existing valve cover bolt hole near the number 1 cylinder spark plug hole. With the base in place, set your dial indicator into position, with the pointer resting on the top of the valve spring retainer. In our shop, we have found the lobe center method of cam degreeing to be the most effective approach. Cams that have been degreed in increase performance by an average of 4 to 5 horsepower over the same cams that use the standard stock timing marks. The process of cam degreeing allows you to know exactly where the opening and closing points of your valve are in relation to the crankshaft for optimum performance. The proper starting position to zero the dial indicator is with the heel of the cam facing the rocker arm. Using the number 1 cylinder on the exhaust side, set your indicator with the stem of the indicator parallel to the valve stem and perpendicular to the retainer. Make sure the rocker arm will not hit the indicator when the engine is rotated. With the valve fully closed, set the indicator at 0, approximately halfway through the travel of the indicator. Slowly rotate the engine in the direction of running until the needle of the indicator reaches 50 thousandths. Stop at this point and take a reading from the degree wheel, which in this example is 49 degrees before bottom dead center. Continue to rotate the engine in the same direction until the valve is completely open and then begins to close. At 50 thousandths before the valve is fully closed, stop, take a reading from the degree wheel. The reading in this example is 19 degrees after top dead center. Now add up the 2 readings you have obtained from the degree wheel. Add an additional 180 degrees to the total and then divide by 2. From this total, subtract the smaller of the 2 readings you have obtained from the degree wheel. The resulting number is your lobe center. In this example, our first reading was 49 and our second reading was 19, which adds up to a total of 68. Add 180 to 68 and we get a new total of 248. Divide that number by 2 and our result is 124. Now we subtract the smaller of our 2 original readings, which in this case was 19. The final result is 105, which is the lobe center in this example. We should add a note of caution here. When determining the lobe center, never rotate the engine in the opposite direction. If you accidentally pass your reading point, continue rotating the engine in the same direction until your reading comes up again. Now that you have found the lobe center, you need to adjust the cam to obtain the recommended lobe center. For this particular engine, the recommended setting is 108 degrees. Rotate the engine until the cam sprocket bolt is in a position to be loosened. Loosen the cam sprocket bolt and nudge the engine in the opposite direction of normal rotation. If your lobe center is larger than needed, you will need to rotate the engine in the normal direction. Remember, you only want to move the engine a few degrees, and with the bolt loose, you will be able to see the sprocket move while the cam stays stationary. In this case, approximately 3 degrees. Retighten your cam sprocket bolt and repeat the degree process as before. After taking your readings again, you will know if the cam needs further adjustment. With the recommended setting of 108 degrees, the opening point will be 52 degrees before bottom dead center, and the closing point will be 16 degrees after top dead center. When the cam is in the proper position, install the other cam bolts and torque. Make a note to use Loctite on all cam sprocket bolts. You are now ready to degree in the intake cam. After finding your initial settings, you will be able to adjust your lobe center to the recommended setting by following the same procedure as the exhaust cam. With the intake cam set at 108 degrees center, the valve opening will be 16 degrees before top dead center, and the valve closing will be 52 degrees after bottom dead center. Do not remove the degree wheel from the engine or move the pointer. You will need these for ignition timing. Install the ignition plate on your engine and wire the coils. Position your engine at 34 degrees before top dead center on cylinders 1 and 4. Scribe a mark on the advance units that will be a permanent reference mark for 34 degrees ignition timing. Rotate the engine to 34 degrees before top dead center on cylinders 2 and 3 and repeat the procedure. With Suzuki motors, we use 34 degrees of advance, and with Kawasaki motors, we use 36 to 38 degrees of advance. Now that the advance unit is marked, the degree wheel may be removed. The engine is ready for strobe light timing at 4,000 RPM later on. Now that the degree wheel and the dial indicator have been removed from the engine, the ignition plate can be bolted into place using the center position of the adjustment slots. With the ignition plate in the middle position, precise engine ignition timing can now be set with a strobe light. With a standard Vance and Hines exhaust system, 33mm smoothbore Mikunis, and the parts and modifications we have been reviewing in this video, we are now ready to subject our 1168cc engine to a dyno test. The ignition timing was checked with a strobe light, and the engine broken in on our dyno for approximately 20 minutes. Then we made test runs at 8, 9, and 10,000 RPMs. You can see the results for yourself.
So there you have it, the information you need to build a high-performance engine. All of the high-performance parts and machine work shown here are available from Vance and Hines. The clearances that we have recommended are used here at Vance and Hines when we assemble a high-performance engine. The required tolerances and clearances for your applications may be different. Use your shop manual or performance parts instructions as a reference. Your local machine shop can perform some of the operations we've been discussing. If you need further assistance, call or write to Vance and Hines Racing. We'll be glad to help.